I'm not sure what I did to deserve that applause, but thank you for coming, and welcome to the inaugural lecture, the inaugural Stephen Hawking lecture. And this is courtesy of the Black Hole Initiative and the Stephen Hawking Foundation. And the idea of this, which we hope to be an annual lecture series, is both to bring inspiring scientists here to lecture and also to pay tribute to Stephen Hawking, one of the great scientists of our time. Now, Stephen had a huge intellectual influence on many physicists and others at Harvard, and he was also a friend of Harvard's. He came here many times. He collaborated with many people here. Here's a picture of him in 1982, getting an honorary degree here. He gave the Loeb Lecture in the physics department 3 times. I think that's a record number of times. Made a lot of money off his first lecture. He made it into a book, The Brief History of Time, which sold many copies. Here he is in Sanders 5-10 years ago when he was giving a lecture at the inauguration of the Black Hole Initiative. And so we wanted to bring an inspiring scientist to give, especially for the first inaugural lecture, and nobody could be more appropriate for that role than today's speaker, Kip Thorne, who was both an intellectual friend, collaborator, and longtime personal friend of Stephen Hawking's. And so now I will turn it over to the director of the Black Hole Initiative, Peter Gallison, to introduce Kip.
It's an enormous pleasure to welcome Kip Thorne today to Harvard and to be the first and inaugural lecturer in this series. It's perfect, as Andy said, on many grounds. It's perfect because what Kip has done over a lifetime of contributions to physics is to make general relativity and black holes vivid in a way to us within the technical community of those who work and research in this area and to an immensely broader public. His contributions span such a wide range in general relativity. I only want to mention a few, but they have certain things in common because you can think of Kip Thorne as a theory engineer. And by that I mean not just theoretical engineering, but somebody who takes the sensibility of making things, of building things, into the heartland of theory itself. When he imagined the conditions under which stars or entities could collapse to form a black hole, he pictured a hoop in his famous hoop conjecture wrapped around the critical circumference and spun on its axis. If everything was contained within that, it could collapse. He had ideas about the membrane hypothesis or the membrane conjecture that redescribed black holes in terms of a thin surface substituting just outside the horizon. This gave rise to many different insights into the nature of general relativity and black holes. He loved visualization and loves visualization in all of its manifestations. I remember once visiting him at Caltech, and he couldn't wait to open his computer and show me these new visualizations of black holes and their merging and how they could be visualized in a novel way. He's perhaps known to anybody who's studied general relativity through the book that he and others know, the Misner, Thorne, and Wheeler, this immense tome that's saturated with images that show you as if general relativity and all of its manifestations were forms of machinery, things that could be imagined, vectors penetrating sheets and ringing bells, and you could picture this in a way that left a vivid impression on all those who worked with this extraordinary volume from the early 1970s. And of course, he's known to all of us through the work for which he shared the Nobel Prize in Physics for LIGO. This is one of the most beautiful and extraordinary experiments in the history of science. It is remarkable, and remarkable on so many different levels that one can only begin to count the ways. He began work and co-founded the LIGO collaboration in 1984. They discovered the first black hole merger was in September 2015. For all of those decades, Kip and his colleagues and an increasing number of generations of physicists participated in this remarkable experiment, able to hear black hole mergers 1.3 billion light years away. It's a beautiful experiment and still expanding. It works by having coincidences of events, first in Louisiana and Washington State, and then later there are new sites in Italy, Japan. It's become a world-covering experiment that was envisioned so many decades before it was realized that it really took an act of faith and imagination to be able to back and devote that much effort to it. And Kip's ideas were not just present in the launching of this. He was involved in imaginative discoveries that were really engineering, scattering light and suppressing it inside LIGO, in new techniques for reducing thermoelastic noise, one of the dreaded noise sources in the apparatus. He was involved in so many stages of picturing this new apparatus and this new way of grasping the universe, not through electromagnetic radiation, but through gravity waves. His work, in his description, his own description of this lecture that we're about to have the pleasure of seeing, he described exploring and imagining as the two sides of what he's done. And they've really come together in every stage. He brought visualization, imagination, and deep insight into physics, into all the techniques and theoretical developments, new mathematics and engineering applications across the decades of his work. And then he took the whole thing and flipped it the other way and used his grasp and insights into general relativity to make one of the most scientifically interesting films that functions as well as entertainment on the big screen in Interstellar. For these and many other reasons, there could be nobody more perfect to welcome here to Harvard today, guest of the BHI, friend of Harvard, Kip Thorne.
I would like to begin with a quotation from my dear friend Stephen Hawking. Can you hear me? Okay, good. That was no overly generous introduction, Peter. Thank you very much. I'm going to prop my computer up here for the first part of the talk because I actually have some notes here that I want to rely on for the first rather carefully crafted part of the talk. And I also need to change to another pair of glasses in order to see my screen properly. Just a moment. Okay. So in 1962, I went to Princeton for graduate school with the express purpose of working with John Wheeler, being mentored by him. He was the great guru of that era in the field of Einstein's relativity theory, which I had decided already when I was 13 years old was what I wanted to work on when I grew up. From Wheeler, I learned that our universe might have a warped side. At least that's what I call it now. We didn't call it that then. By this I mean it likely contains objects and phenomena that are made from warped space-time instead of made from matter like you and me. Examples are black holes, gravitational waves, the Big Bang, vacuum fluctuations, whatever that means, I'll explain that later, wormholes, and time travel. Now, the warped side of the universe has been the focus of most of Stephen Hawking's career and of my career. And over the subsequent half century, since John Wheeler introduced it to us, it has been what Stephen and I have focused on. We met in London in 1965 and quickly became close friends, and over the next few years, our careers diverged from each other. Stephen moved in the direction of the quantum mechanical aspects of the warp side of the universe. For example, tiny black holes that are governed by the laws of quantum mechanics instead of classical physics, the evaporation of black holes, and the laws of quantum gravity that control the merger between general relativity and quantum mechanics. I, on the other hand, moved into astrophysical aspects of black holes and gravitational waves. And let me make a remark about why I did that. I think that the direction Stephen chose was the much more important direction, the much more exciting direction. However, my mind works slowly. I learned that when I arrived at Caltech as an undergraduate, and I had a real struggle for the first year and a half because I was much slower at grasping things than the other students. I had to figure out ways to learn them better and more solidly in order to survive. So I needed more elbow room in order to be able to really do what I wanted to do. So I chose areas in which almost nobody else was working, whereas Stephen boldly went into the areas that were far more popular. So as a result of this divergence, our friendship quickly became a very personal friendship rather than a physics friendship. And when we would get together, we would be more likely to talk about our lives, our loves, and even death, which Stephen did talk about as he saw with his motor neuron disease. He thought in the early 1970s he would not live beyond 1980, that he would die of pneumonia by 1980. And so he became very rushed in his career because of that. Stephen had a profound impact on me personally. But more importantly, he had a profound impact on human understanding of the universe. It was a huge inspiration for so many people, scientists and non-scientists, adults and children, through his George books for children that he co-authored together with his daughter, Lucy Hawking. Amazingly, despite his motor neuron disease, he lived beyond 1980. He lived, in fact, to age 76, in part, I think, due to his zest for life, as epitomized by him floating in free fall in the so-called vomit comet in the upper picture. It was an aircraft that would shut off its engines and go into a parabolic orbit up, over, and down so he could be in free fall. Or our trip to Antarctica together in the Antarctic winter. And the other photo is of him lecturing about the universe. So it was partly his zest for life that got him through to age 76, but also his extreme stubbornness. He was the most stubborn person I ever met in my life, and that stood him well. We lost him on March 14th, 2018. It was a terrible loss, and I'm so very pleased that Harvard has established this lecture in his memory. It's a great honor for me to have been chosen as the inaugural BHI Stephen Hawking lecturer, and I thank you very much. Let me move on then. And I want to begin talking about the warp side of the universe with this image of the black hole Gargantua as it appears in the movie Interstellar, which I was deeply involved in from the very conception of the movie onward. Why does this image of the Gargantua look like this? Well, you can understand it by the following, that the black hole is surrounded by a disk of hot gas, much like the rings of Saturn. We call it an accretion disk of gas that's gradually spiraling into the black hole. And if a light ray or a photon, a particle of light, is emitted off the back upper face of the disk, it is pulled by the black hole's gravity up over the black hole and down to the camera. And so it produces the upper part of the image. And the light rays like that produce the upper part of the image. And light rays that go from the bottom back face under the black hole and up the camera produce the bottom part of the image. And light rays from the front of the accretion disk produce the crossbar. So it's a very simple explanation of why it looks like that. And the image of this black hole and the images of wormholes and most everything that you see of that sort in the movie, these are actually from computer simulations based on Einstein's equations that were done with me feeding the equations and necessary data to Oliver James at the DNEG computer graphics company, and him working together with his colleagues then to make the image based on general relativity. Now, in 2019, the Event Horizon Telescope, of course, observed the first black hole that astronomers had ever directly observed, the black hole in the M87 galaxy. I remind you that this is a collaboration of about 400 scientists and engineers at 100 institutions led by Shep Doleman here at Harvard and headquartered here at Harvard. It combines the data from many radio telescopes worldwide, data at 1.3 millimeter wavelength, and combines those data coherently to make an image as though they had a telescope that was the size of the Earth. And this is the first image that they saw. And from the size of the black hole in the center, that's the shadow of the black hole's horizon against hot gas that is being emitted, but being blotted out by the horizon in front of it. And knowing the distance to M87, they inferred that the first black hole they saw weighed 6 billion times what the sun weighs. Just fantastic. Now there's Gargantua and there's M87. And many people have commented on how similar they are. Well, I think they look a lot different, and why? Well, first of all, on the right-hand side of M87, it's much brighter than on the left-hand side. Why is that? Well, it's because of a Doppler shift. The gas on the right-hand side is moving toward us. The gas around the black hole, the gas on the left-hand side moving away. So the Doppler shift makes the right-hand side brighter and less red than the gas on the left-hand side. And I said to Christopher Nolan, now we have to put in the Doppler shift when we make our image of Gargantua. And Chris said, no. We want this to be realistic. And that's not realistic. I said, well, of course it's realistic. And Chris said, no, the human eye cannot distinguish at all well levels of brightness or even color when it's looking at something as bright as this is. And so we want something that sees it in the movie like the human eye would see it, and so we don't put in the Doppler shift. Okay, so that's the first part, explanation of the first part. The rest of the explanation is in this little film clip from Oliver James, who is the chief scientist at the double negative or DNEG visual effects company that did the visual effects and got the Academy Award for the visual effects in Interstellar. He says, let's just move our camera from just above the plane of the accretion disk to the North Pole. And obviously, this is what we get when we move the camera. And then we fuzz this out because the radio astronomers have far less good resolution than we do in the movie. And so you get that, and then we'll put in the red shift and blue shift. However, that is partially a cheat for a very important reason. That is that the gas, in the case of M87, is not in a thin accretion disk. It's moving in a much more interesting three-dimensional manner. And that's precisely what I'm eager for the EHT collaboration to do, is to make movies. In the case of the black hole in the center of our own galaxy, where the time scale for the changes is much faster, make movies that show us that gas flow, which will be really very interesting observationally and astrophysically. Let me move on. The key thing for my lecture, however, is that black holes are made from warped space-time. So that, for example, the circumference of this black hole is much smaller than its diameter. You look at it, how can that possibly be? And the answer is because space is warped around and inside a black hole. I use an analogy. Let's take a rubber sheet, a child's trampoline, put it up on high sticks, high poles, and put a rock in the center, and then the rubber will bend down, as you see here. And then imagine you are an ant. You're a blind ant, so you can't really see what's going on here. But you have a degree from Harvard, so you are really intelligent. And so you march around in a circle around here, and you measure the diameter, the circumference, and then you march down here measuring the diameter. By the way, this is the rock down there. And you come back up, and the diameter is obviously huge compared to the circumference. And so even though you're blind, you can tell immediately that your universe, which is that rubber sheet, is warped. It's not flat. Precisely the same diagram holds for a black hole. I just changed the labels. Now we're talking about a two-dimensional surface through the black hole, since the black hole is really three-dimensional. And we're talking about it's being bent in a higher dimensional space, which may or not really exist. The physicists would call the bulk. That's called the fifth dimension in the movie Interstellar, because the fourth dimension is time. You have east, west, north, south, up, down. That's three space dimensions. You have time, and then you have the fifth dimension, which is going out into the bulk. So this is bent in the bulk in that manner. The thing that we all know about black holes, of course, is that if you fall into a black hole, you can't get out and you can't send signals back out. So here I am, a little two-dimensional Kip on the surface of this, because remember, the surface of this is our universe. And it looks two-dimensional, but it's really three. And I fall through the horizon, and thereafter both I and the signals I'm trying to transmit to you with a microwave antenna are pulled willy-nilly down to the singularity where I die, and the atoms of which my body is made get distorted and crushed, according to the theory, which I'll return to in a little bit. Then, in addition to the warping of space, there's a warping of time around the black hole. Time slows to a near halt near the horizon. In the movie Interstellar, on a planet that is very close to the horizon called Miller's Planet, 1 hour on Miller's Planet is 7 years back on Earth. And that's a story in and of itself, but you have to read my book, The Science of Interstellar, to get that story. So 1 hour on Miller's Planet is 7 years on Earth, and then below the horizon, what happens to time, and what is slower than stopped time, if time stops at the horizon? Time actually flows in a direction you would have thought was a spatial direction. It flows down toward the singularity at the center. And that's the second reason that you cannot get out of a black hole, that you cannot move backwards relative to the local forward flow of time. That's utterly impossible. In addition, black holes spin. All black holes, or certainly almost all black holes, spin on an axis like the Earth spins. That drags space into a whirling motion. This is a whirling motion that you can measure with gyroscopes. You can see that an inertial direction is defined by a gyroscope, twists around and around when you're near a black hole. So that's like space whirling around and around in motion around the horizon. Fast near the horizon, slow farther away, sort of like the air in a tornado. So this is a precise depiction for a fast-spinning black hole of the shape of space. The horizon down here looks like a circle, but remember I have to restore the missing dimension so it becomes a sphere, really a flattened sphere. The color coding shows the slowing of time. Time flows at a rate of 10% of what it is far away at this location close to the horizon. And the angular velocity of the dragging of space into motion is proportional to the length of those wide arrows. Now, what warps the black hole space and time? The answer is the energy contained in the warping. Imagine this rubber sheet that I talked about. If you push on the rubber sheet, you put energy into it. You have to do work in order to push the rubber sheet down. In the same way, it takes a huge amount of energy to warp space around a black hole. And the energy in that warping produces gravity. It produces space-time curvature. It produces precisely the warping that you see. So the black hole is held together by what a physicist would call a nonlinear self-interaction. It's what a physicist would call a gravitational soliton. Now, if my wife, Carol Lee, is at the north pole of this black hole, then a gyroscope at her feet twists around and around at a very high speed because it's close to the horizon, but the gyroscope in her head is going around much more slowly. So her head, see her feet going around in a counterclockwise direction. If you think about it, her feet see her head going around in a counterclockwise direction. It's like you take a wet towel to squeeze water out of it, and you wring the wet towel. If your left hand sees your right hand go counterclockwise, your right hand sees your left hand go counterclockwise. So there's a counterclockwise twist of space near the North Pole, and a clockwise twist of space near the South Pole. I like to call these vortices of twisting space. Now, for physicists, These vortices are a visualization of what is called the frame drag or gravitomagnetic part of the Riemann curvature tensor. So this has a grounding, a precise grounding for physicists or mathematicians in the properties of this object called the Riemann curvature tensor, which is central to general relativity theory. Now, non-physicists, you ignore that remark, and we'll move on. Okay, so tidal gravity. If we have the moon, it pulls on the Earth's oceans and produces the tides. The ocean toward the moon bulges up. The ocean away from the moon bulges down in this direction because of the difference in the gravitational pull on the near side and the far side. And that's the direction of the gravitational pull on the sides of the moon. The center of the Earth doesn't feel any gravitational pull, in fact, because it's falling freely. So if I just subtract the arrow that would be associated with the center of the Earth, what the Earth itself feels as it falls freely is just a stretching and a squeezing, stretching toward and away from the moon and a squeezing on the sides, and that produces the tides in the Earth's oceans. In general relativity, it turns out that if you look at the mathematics of this Riemann tensor, and you look at the tidal part of the Riemann tensor, and you look at its visualization, it turns out there are things that I like to call tendices, or a stretching tendex that sticks out of the moon, and it grabs hold of anything there and stretches it. It could be a person, as I show here, or it could be the Earth's oceans. And there's a squeezing tendex that is going around the moon that squeezes these. And these tendices are things that my student, I shouldn't say after I retired, I had the pleasure of collaborating with other people's students. And other people's students that I was collaborating with after I was done mentoring students, they discovered this in the mathematics of general relativity after seeing it in computer visualizations. For physicists, then, the tidal part of the Riemann tensor is the thing that underlies the tendex, the stretching tendex and the squeezing tendex. For a black hole, similarly, the black hole has a stretching tendex and a squeezing tendex, which stretch and squeeze Miller's planet and produce phenomena that you see in the movie associated with Miller's planet, the water planet. Now, again, for physicists, because this is not familiar, even to the physicists who work in relativity probably, for vortices, tendices, and underlying frame drag and tidal parts of the Riemann tensor, you have to go to my textbook, the one I wrote with Roger Blanford recently. This is not in the original Misner, Thorne, and Wheeler. In either of these two textbooks, it's the same section. It's boxes 25.2 and so forth. And you'll see all the mathematics there and the precise visualizations. Now, I want to talk about the interior of a black hole rather quickly. In the movie Interstellar, Cooper plunges through Gargantua's horizon and into the interior of the black hole. I want you to watch carefully what you see above Cooper as he looks out the window, as he's falling through the horizon.
Approaching the event horizon.
Okay, so he's approaching the event horizon. If you look here carefully, the black hole is on this side, and the external universe is, of course, outside of the ring. This is the accretion disk as seen from this Ranger spacecraft as it's falling into the black hole. Now let's go on and watch happens after he goes through the horizon.
Port side, dipping down beneath it to go through it.
Now the black hole appears to be subtending most of the sky, and the external universe is in a small patch in the interior of the accretion disk. And that's the way it really looks. That's from a computer visualization. And it also really hammers home the fact that if you're inside a black hole, you see the external universe just fine, because light can fall into the black hole after you. But if you're outside the black hole, you can't see in at all. It's a one-way membrane. Now, inside the black hole, it turns out, as best we understand it, there are three singularities. There is a chaotic singularity down here at the center, which in which if you fall into it, you get stretched and squeezed in a chaotic manner, first in one direction and then another direction, then another direction, and ultimately you die. The atoms which your body is made get stretched and squeezed, and we don't know what happens in the end because the core of the singularity is governed by the laws of quantum gravity. For physicists, this is the so-called BKL singularity. There's also an infalling singularity. Time is so screwed up inside the black hole that if Cooper, falling into the black hole in his Ranger spacecraft, is there, as he looks up above him, everything that falls into the black hole after him over billions of years, he sees coming crashing down in a fraction of a second in a thin sort of shock wave behind him, a singularity that is a smashing singularity. That is sometimes called by physicists the mass inflation singularity for obscure reasons. And then there is also an outflying singularity. Everything that fell into the black hole before him, a little bit of it scatters back up and is seen to come crashing up at him in a sort of a shock wave. Cooper in the movie hits this shock singularity. And his Ranger spacecraft, you see in the movie, it falls apart and he is thrown out of it. But what is not really described in the movie very carefully is that he is then scooped up by a four-dimensional spacecraft and deposited in the three-dimensional face of the four-dimensional spacecraft. It's a spacecraft that is provided by a civilization that lives in the bulk. And he travels back across the bulk to the Earth. And if you want to understand that, well, let me just say that Christopher Nolan and I, early in working on this movie, he said, I want an ending that is as difficult to understand as the ending in Stanley Kubrick's movie 2001: A Space Odyssey. He succeeded. And then he said, I know you're planning to write a book about the movie. You can explain the ending in your book. The only way you're ever going to understand the movie is to buy my book and read section 7 on the climax. There are 5 chapters to explain the ending of the movie. Okay, let me move on. I want to conclude my discussion of black holes by an extract, an animated extract from my book with Leah Halloran called The Warp Side of Our Universe. Leah is a fabulous painter, a young painter that I met roughly a decade ago. And she and I have collaborated my attempts at verse, at poetry, tightly integrated into her paintings. And this just gives you a flavor of a bit of this.
What is Felicia? She's the sum of all her parts. Her face, her silken hair, her arms and breasts, her hands and legs and feet, her heart, her brain, her precious personality. And what is a black hole? It's the sum of all its parts. Its space that is warped, the funnel of bulk being seas, its vortices of whirling space, its tendencies that stretch and squeeze, its slowing time and down cascading time, its horizon and its singularities, all made from warped space-time.
So let me move on to gravitational waves. And let me also make a remark that later in this lecture, a lot of the images that you will see are paintings by Leah Halloran, because I have found my collaboration with her to be really good at stimulating me to find new ways to talk about some of this physics, and her paintings are powerful tools for that. Gravitational waves were first predicted by Albert Einstein in 1916 based on his general theory of relativity, which he had devised just a few months earlier. I like to describe a gravitational wave in terms of the tendencies. A set of tendex lines that stretch horizontally, and a set of tendex lines that squeeze vertically if the wave is propagating into the screen. So the stretch and squeeze are in planes orthogonal to the propagation direction, and they are out of phase. So space, or inertial frames if you have it, you want to think about it, stretch and squeeze like that. So 2 inertial frames, one here and one there, things that are moving inertially, like particles that are just at rest before the waves arrive, get pushed apart, then together, and apart and together, and out of phase in the other direction. A Tendex, which I've talked about before, is actually a collection of Tendex lines that do the squeezing along some particular direction, a direction along which the squeezing is particularly large or stretching is particularly large. Now, as best we understand it, there are only two types of waves for exploring the universe. They can be created in the distant stretches of the universe, travel across the universe to the Earth, and bring us information about what's far away. Electromagnetic waves, which of course include light, radio waves, X-rays, gamma rays, and so forth, and gravitational waves. And it was Galileo, about 400 years ago, who built his little optical telescope, pointed it at Jupiter, and discovered Jupiter's 4 largest moons. And thereby he initiated instrument-based electromagnetic astronomy, which over the ensuing decades and centuries has completely changed our understanding of the universe around us. In 1972, stimulated in large measure by Ray Weiss, my students and I and some colleagues had a vision for creating gravitational wave astronomy and began to do the best we could to estimate how strong the waves would be and what kinds of things we could do with the gravitational waves as astronomers if they could be detected. Ray was at MIT. He was the primary inventor of the gravitational wave interferometer, we call it. You have two mirrors that hang from overhead supports along this arm of an L-shaped configuration. These two hang from overhead supports. When the gravitational wave comes in from above, it stretches these apart while squeezing those together, then pushes these apart while squeezing those together. And that differential motion along the two arms is measured using laser beams by a technique of laser interferometry that I won't go into, but that many of you know about. Now, gravitational waves are made from the same thing as black holes, from warped space-time. And so they, in fact, are the ideal tool for exploring objects that are made from warped space-time, that is, for exploring the warped side of the universe. For 43 years, a very large team of physicists and engineers worked very hard to develop and perfect Ray Weiss's concept for the gravitational wave interferometers. I should say his concept as elaborated and improved by Ron Drevers and a few other people who made significant contributions to the design. This 1,000-person LIGO team was organized and assembled by Barish at Caltech, and initially led by him until he went off to lead the design of the International Linear Collider and turned the leadership over to J. Marks and then to David Wrightsey. This 1,000-person team designed and built advanced gravitational wave interferometers after having built a family of initial interferometers. They then built and designed the advanced ones and developed the data analysis algorithms that ultimately had success in 2015. In parallel, there was a big effort to develop the tools for simulating on computers the collisions of black holes. And this was motivated in the later years by LIGO, because it seemed very likely to me that the first thing that we would see would be gravitational waves from colliding black holes, and we could not even predict the details of the waves from the merger of the black holes without computer simulation. We just were not clever enough to solve Einstein's equation to determine that. And that 60-year effort, on one hand, by the computational physicists, and the experimental effort, the 40-year effort by the experimental physicists, they came together pretty much at the same time, each reached fruition at more or less the same time in 2015. And LIGO's first gravity wave signal that arrived in 2015 from colliding black holes, then were emitted 1.3 billion years ago. This is from the computer simulations for that particular signal. This is what the black holes were doing, the shape of space and the warping of time around the black holes. The Funnels are the black holes, like I showed, sort of funnel-like warping of space. The color coding is the slowing of time. Where it's black down inside, that's the interior of the black hole. Where it's red, time is much slowed. This went into slow motion, and then we pause it at the moment of collision, and there's a great splash, a huge distortion of space, a huge oscillation in the rate of flow of time, and a burst of gravitational waves went flying out into the external universe. Now, those gravitational waves, or that movie does not begin to convey the richness of this black hole collision. It's only showing you a small piece of it. It's showing you the warping of space and the warping of time in the orbital plane of the black hole. There's much more to it than that. And so I want to show you what the tendencies that stick out of the black holes are doing during the collision. And so in order to do this, I go back to a three-dimensional drawing, a painting by Leah Halloran that is in our own universe. Before you were seeing this as seen from the bulk. It was the warped space-time as seen from the bulk. Here we're looking in our own three-dimensional universe. There you see the horizons of the two black holes. They have just merged. And sticking out of the merger region, there are tendencies that squeeze radially, and the corresponding tendencies that stretch circumferentially. Sticking out of the ends, there are tendencies that stretch radially and squeeze tangentially. And as the two black holes orbit around each other, these spray out backward like water from a whirling sprinkler. And so you get these spiral arms, these four spiral arms, and that becomes one part of the gravitational waves, but not the whole story. There are also, if this black hole is spinning, there are vortices, or twisting space, that stick out of the black holes. Two vortices, one here and one there, sticking out of this black hole. We're now looking at this, again, a painting by Leah Halloran. These are Leah's paintings. These vortices sticking out of this black hole and two vortices sticking out of that black hole, and as seen from the bulk, from the higher dimensional. And they spray outward because of the orbital motion of the black holes around each other, like this. Now, those vortices are not what we think of as gravitational waves, because they're twisting space. They're not stretching and squeezing. But these outflying vortices generate, entwined with themselves, tendencies that stretch and squeeze. And so here you have the tendencies wrapping around the vortices. And those are the gravitational waves that we are all familiar with. For physicists, the vortices are embodied in the so-called frame drag part of the Riemann tensor. The tendencies are embodied in the so-called tidal part of the Riemann tensor. The so-called Bianchi identities of general relativity look like Maxwell's equations. Just as a moving magnetic field generates an electric field, so moving tendencies embodied in this guy generate moving vortices generate tendencies. And so there's a remarkable connection, or similarity between Maxwell's equations and general relativity here that I only came to appreciate by seeing this in computer simulations and then going back to the mathematics and seeing how it comes out of the mathematics. Well, let me move on quickly. The gravitational waves generated then 1.3 billion years ago moved out of the galaxy in which the black holes lived into intergalactic space. They traveled across the intergalactic space for 1.3 billion years. 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals, that burst of gravitational waves reached the outer edges of our Milky Way galaxy. On 14 September 2015, the burst of gravitational waves hit the Earth in the vicinity of the tip of the Antarctic Peninsula. They traveled up through the Earth unscathed, unaffected by all the matter inside the Earth. They came up through the Earth at Livingston, Louisiana, where we had one LIGO gravitational wave detector with its arms that got stretched and squeezed by the waves coming out of the Earth. And then 7 milliseconds later, 7 one-thousandth of a second later, they came up through the Earth at Hanford, Washington, and stretched and squeezed the arms of that gravity wave detector. It took 5 months for the 1,000-person team of LIGO scientists and engineers, together with collaborations from a gravity wave detector group called Virgo, that was a French, Italian, Netherlands collaboration at the time, well, I guess with some contributions from Poland and Hungary. They had built their detector, but it was not yet fully operational. And so the two teams together analyzed the LIGO data, and it took 5 months to be absolutely sure that what was being seen was gravitational waves before the results were announced. This is the cleaned up signal in, you call it the cleaned up signal in gray, stretching and squeezing as a function of time. And the red is from a computer simulation by the so-called SXS numerical relativity collaboration. That was a Caltech Cornell collaboration, largely at the time. And by comparing the computer simulations with the observations, it was possible to infer that the initial black holes weighed 29 and 36 solar masses for a total of 65. The final black hole weighed only 62 solar masses. That's as though 3 solar masses had been, as though 3 suns had been annihilated and turned into gravitational waves in a fraction of a second. So the power output, the energy per unit time, turned out to be 50 times larger than the total power from all the stars in the universe to put together, sending out light. So 50 universe luminosities for a fraction of a second, producing these gravitational waves, and inferred that the distance of the source was 1.3 billion light years. Now, LIGO by now has seen more than 200 black hole collisions, and LIGO scientists are exploring the black hole laws, the properties and populations of black holes in our universe, together with the Virgo scientists, and now also with a gravitational wave detector team in Japan called CAGRA. They've seen several collisions of neutron stars, several black holes being swallowed by swallowing neutron stars, and they're in the process of exploring the warp side of our universe with gravitational waves. The holy grail of this will be to explore the Big Bang birth of our universe using gravitational waves. And I'm hoping that that happens before I pass away. I plan to live to 110. So that's sort of an upper limit. But for those of you who are working on this, just keep that in mind, please. Let me now turn, as I move into the last part of my talk, to vacuum fluctuations in the warp side of the universe. This is not something that I talked about until the last year or so. It was really only through my collaboration with Leah Halloran, the painter, that I somehow was stimulated by our conversations to realize how important vacuum fluctuations really are in the universe, as well as, and that the manner in which the universe and possibly advanced civilizations manipulate these vacuum fluctuations is a stimulus for, an inspiration for modern quantum precision technology, where my LIGO colleagues are manipulating vacuum fluctuations for high precision measurement. So that's where I'm going. I want to begin with Yakov Borisovich Zeldovich, a very close personal friend of mine who happened to be one of the 2 so-called fathers of the Russian hydrogen bomb. Shortly after he left the hydrogen bomb project in Moscow, he got into astrophysics. I became a close friend of his. He invited me to Moscow on a number of visits. And on one of these visits, I took Stephen Hawking with me. And in that visit, Zeldovich described the importance of vacuum fluctuations to us. So this is Leah's depiction of vacuum fluctuations. What they really are is the following, that if I begin with a box and I remove everything that possibly can be removed, then because of the uncertainty principle of quantum mechanics, the so-called Heisenberg uncertainty principle, you inevitably are left with tiny fluctuations of everything that could have been inside the box. Tiny fluctuations of protons, electrons, photons, gravitons, all fluctuating in and out of existence in a random sort of a way. It's a minimum that can be left. These fluctuations have, at least for the purpose of this lecture, no energy and produce no gravity. In reality, they may well be the source of the so-called dark energy in the universe, but I'm not going to talk about dark energy. And dark energy has such small amounts of energy in it that for the purposes of my lecture, I'm going to just ignore it and imagine these vacuum fluctuations have no energy and produce no gravity. September 1973, these are again Leah Halloran's paintings. September 1973, I took Stephen Hawking to Moscow. We were in the Hotel Rossiya, and Yakov Borisovich Zeldovich and his young colleague, then Alexei Starobinsky, came to talk with us. And Zeldovich and Starobinsky described to us the following process that they asserted happens. That if you have a black hole, it will always be bathed by vacuum fluctuations. There's no way to avoid it. And these vacuum fluctuations, which Leah shows here coming in from the left, though really they bathe it from all directions, they have voracious appetites. And they suck energy out of the vortices of twisting space around this spinning black hole. And they use that energy to transform themselves into real particles of outgoing radiation. And as a result, they suck energy out of the spin of the black hole because the energy in the vortices of twisting space is really ultimately tied to the spin of the black hole. And so the black hole gradually spins down, and we don't see the vacuum fluctuations normally. You have to work very hard in order to be able to see them experimentally, but you can perfectly well see the outflying radiation. And so it just looks like that spinning black hole radiates, and as a result, radiation spins down. Stephen Hawking and I were a little skeptical. I was very skeptical because I knew Zeldovich well and knew that he did not know general relativity at all well, but he had a fantastic physical intuition. And so I challenged them, and Starobinsky, who I had not really become acquainted with before, he said, well, I've done the calculation. And he sketched out the calculation. It was very believable. I came to respect him enormously. Stephen went back to Cambridge, England, and he thought about this, and in December, just a few months later, he had an epiphany, a sudden insight, in which he realized the following, that if you have a non-spinning black hole, and it's imploding, as it implodes, it will create at its center, a non-spinning star. And the star implodes. It will create at its center a black hole, and as the star continues to implode, the black hole will grow. The surface of the black hole expands at the speed of light relative to inertial frames there. And that expansion of the horizon and the space in the vicinity of the horizon at the speed of light has a lot of energy in it. And vacuum fluctuations then coming in from all directions, though Leah just shows it from one direction, to the vicinity of the horizon, they suck energy out of the expanding space around the horizon and turn themselves into real particles of radiation that go flying outward. This is what we now call Hawking radiation. The remarkable thing, the really surprising thing that Hawking asserted in his paper on this is that even 1 billion years after the black hole was born, there's still Hawking radiation leaking out of the vicinity of the black hole from the era of its birth. In fact, that is now pretty universally accepted, but only after other people and also Hawking and Jim Hartle did calculations by other methods to verify it. But this is how Stephen first discovered it, stimulated by Zeldovich. Back in 1971, Zeldovich also began thinking about what role might vacuum fluctuations play in the birth of our universe. Now here he was rather off base. Now for physicists, his issue was that he somehow imagined that the fundamental equations of physics in that very early era would, like Maxwell's equations, all be conformally invariant. And as a result, with a isotropically homogeneously expanding universe, they could not suck, vacuum fluctuations could not suck energy out of that expansion. Well, Leonid Grishchik disabused him of this and pointed out that Einstein's equations are not conformally invariant in this circumstance. And then, more importantly, a few years later, Alexei Starobinsky, Zeldovich's student, Andrei Linde, who was also in Moscow at the time, and Alan Guth here in Cambridge, and others, developed the theory of the inflationary expansion of the universe, which has this remarkable property that if the universe has this early era when it's expanding extremely rapidly, and then it slows down to a more normal pace, this inflationary era, that it turns out that if then the Big Bang singularity at the beginning produced only vacuum fluctuations, they will feed off the energy of this early, very rapid expansion of the universe to produce all of the matter and radiation that we see in the universe today. And even, it appears, they produce the fluctuations in that matter and radiation that give rise to the birth of galaxies and ultimately to things like Earth and ultimately you and me. So everything comes from vacuum fluctuations. The universe sucks energy out of it in an inflationary era, according to this. And it may well be true. I'm not 100% sure by any means, but it may very well be true. Let me turn finally to wormholes and associate with that the possibility of backward time travel. Albert Einstein and Nathan Rosen in 1935 discovered that the Schwarzschild solution of Einstein's equations, which many of you know about, in fact, if you have no matter present anywhere in the universe, it represents a wormhole that connects two different regions of our universe, or maybe connects two universes together. In the movie Interstellar, it connects the region near the planet Saturn. There's a wormhole. It connects it to the vicinity of the black hole Gargantua in a very distant galaxy. And so here's that wormhole. Remember the surface of this wormhole then, just like the universe itself, it looks two-dimensional, but it's really three-dimensional. It's only the surface that is part of our universe. The higher dimension is the bulk. And so here is the IMAX camera in the movie Interstellar, and down there is are the stars and nebulae and gas clouds, and the black hole Gargantua in the distant galaxy is painted by the team of artists at the DNEG Visual Effects Company. And light rays come up from that distant galaxy through the wormhole to the IMAX camera, and this is the image that you get. And that was the image that is built by solving Einstein's equations with a wormhole like this. But there's a fundamental issue with wormholes. It was a problem that my PhD advisor, John Wheeler, realized just shortly before I went to study with him at Princeton. That is that the kind of wormhole that everybody was thinking at the time, a Schwarzschild wormhole, a wormhole with nothing inside it that is spherically symmetric, that was thought to be just static, just sitting there. In fact, they had not analyzed Einstein's equations fully properly and had not realized, and he discovered it. It actually implodes so rapidly that nothing can go through it and get to the other side. Even a photon traveling at the speed of light gets trapped in the center and destroyed in singularities at that trapping point. And so when Carl Sagan phoned me up in the mid-1980s and said, I'm working on a novel called Contact, and I have my heroine traveling through a black hole to get to the star Vega. I know I might be in trouble. Can you help me? I said to Carl, this is what got me into this business. I said, well, obviously what you need is a wormhole, but you've got to find some way to hold it open. And so I very quickly realized what was needed to hold it open. It turned out that others before me had also realized that. And that is that you have to put into the throat of the wormhole material that repels gravitationally. And I like to just call this exotic matter. So it repels gravitationally and holds the throat of the wormhole open in the process. How can you make exotic matter? Well, it seemed to me that the only way I could imagine doing it is by manipulating vacuum fluctuations. And so together with a couple of my, I guess it was together with Mike Morris, a student of mine, I concocted an example. If you take two electrically superconducting plates, so that even a tiny parallel electric field will drive a current that is so strong that the charges will flow and wipe out that parallel electric field. You take two such plates, then even the vacuum fluctuations with electric fields parallel to the plates will be wiped out. So you'll have lower amount of vacuum fluctuations than you normally do. And as the plates get closer and closer together, you get a reduction in the vacuum fluctuations over a larger region between the plates. And so you get more and more exotic material in the form of modified vacuum fluctuations. And you actually see this, and it's seen in the experimental laboratory. If you hold the plates apart, you discover that there's an attractive force between them. And as they move closer and closer together, the attractive force gets stronger and stronger, and they do work on whatever apparatus you're using to hold the plates apart. This is called the Casimir vacuum by physicists. So let's take two concentric spheres. They look like circles here at the throat of the wormhole. They have the same circumference. They're separated from each other by some distance near at the throat of the wormhole. We charge them up so there's an electric, so that we charge them up so that we can hold them apart with electrical forces. And so we have an electric field that sticks out from either side, holding the plates apart. And then gradually let the plates get closer together, you get more and more exotic material. Now, it turns out that in order to hold the wormhole open, the energy of the material, the energy includes the mass of the material divided by the speed of light squared. That's an energy. The energy of the spheres, including their mass energy, plus the negative energy of the vacuum, the total must be negative in order to hold the wormhole open. And that appeared to me not possible, though I couldn't prove it. Now, in the years since then, as I went off and started to work on LIGO vigorously, because we got LIGO funding not long after that, a number of other people have worked on this problem. And the bottom line today is that I think there's a large consensus that wormholes cannot occur naturally in the universe, almost certainly not, except possibly in quantum foam down at a very tiny length scale. It's called the Planck length. There may be fluctuating wormholes that fluctuate in and out of existence like as part of the vacuum fluctuations and part of the laws of quantum gravity. That may be true. Can wormholes be made by an advanced civilization? Well, if I'm very drunk at a party, I may speculate that an advanced civilization grabs one of these fluctuating wormholes and pulls it out of the vacuum foam, as John Wheeler called it, and turns it into a big wormhole. But I have to be very drunk to think about that. Can they be held open? Probably not. It requires too large amounts of exotic matter. That's the bottom line. But nobody has been able to prove for sure. That's the bottom line of research by a number of people. However, when speculating beyond the frontiers of firm knowledge, I've been proved wrong many times, sometimes spectacularly wrong, as in the case of the so-called dark energy, which I just did not believe existed until it had been seen in several different types of experiments. So don't take my pronouncements that this is not possible too seriously, but that is and has been my position on it, that it's likely impossible. But if I do have a wormhole, then as I discussed in a paper with two students, Mike Morris and Ulrich Yurtsiever in 1988, I put my wife, Carol Lee, she's game to do anything I want her to do in these thought experiments. I put her in a rocket ship and send her out at nearly the speed of light, and then I bring her back to Earth. And it may be a one-year trip as measured by her, but due to the so-called twins paradox, which some of you know about, as seen by me, it may take 50 years. And so I have now aged by 50 years while she has aged by only 1 year. So looking through space, Carol Lee sees me old when she arrives back. However, if we hold hands through the wormhole, during the entire trip. We can look at our watches and we can see that time is flowing at the same rate. So looking through the wormhole, she sees me just having aged by just 1 year, whereas looking through the exterior, she sees me having aged by 50 years. So the wormhole has become a time machine. If I just go over old me, and I crawl through that wormhole into her mouth and come out of my wormhole mouth, I can meet my younger self, back when I'd aged only 1 year. There's Sung-Won Kim and I, and independently Stephen Hawking, and I think some of his students realized, at the moment that it first becomes a time machine, this wormhole may self-destruct. And the issue is that vacuum fluctuations will go flying into the wormhole, through the wormhole, out through the external universe, and back, and arrive back at the very same location and the very same moment as they started out. So you now have twice as many vacuum fluctuations. They began with zero energy. With twice as many, you now have some net energy. And they go through again and again and again, and you have an exponentially growing energy coursing through this wormhole. And does that become enough energy to destroy the wormhole, preventing you from ever making a time machine to go backward in time? This is what it looks like as seen just by Carol Lee and me, with those vacuum fluctuations flying from one mouth to the other in the external universe. Is the explosion strong enough to destroy the wormhole? Stephen and I, this is the one place where our research overlapped quite strongly in our careers in this one sort of crazy issue, but I think very interesting issue. And our conclusion after debating it back and forth was only the laws of quantum gravity know, because at the time that the energy becomes great enough to possibly destroy the wormhole in that process, the techniques that we're using, called quantum field theory and curved space-time, sort of a semi-classical calculation, that fails, and the full laws of quantum gravity come into play, and only then, with full laws of quantum gravity, can you find the answer. But Stephen Hawking, who was fearless, had no fear in proposing a chronology protection conjecture that all time machines ever created by any arbitrarily advanced civilization anywhere and anywhen in the universe will self-destruct as a result of vacuum fluctuations, thereby keeping the universe safe for historians of all species. Let me turn finally to quantum precision measurement technology. It was Vladimir Brzezinski who first pointed out that at some point in the gravitational wave detection process, we would run into the problem that we're trying to measure the motion of massive objects at a level where the quantum fluctuations in their motions will get in the way of the measurement, due again to the Heisenberg uncertainty principle. And LIGO today is at that point, amazingly. We are now monitoring the motions. I should say the team of younger generation scientists who are doing this are measuring the motions of 40 kilogram mirrors to a precision of about 10 to the minus 19 meters, 1/10,000th the diameter of the nucleus of an atom. And that is the level at LIGO's gravity wave frequencies at which quantum fluctuations of the mirror centers of mass get in the way of the measurement. They're producing mirror motions that are at the level of gravity waves at that point. So for the first time, we humans are seeing human-sized objects behave quantum mechanically, and that's one of the remarkable things about LIGO. And as I was saying, it was Vladimir Brzezinski in 1968, a very long time ago, who pointed out that we would come to a point where this would be an issue. And it became clear to me early in the LIGO effort that this was likely to become an issue in LIGO when we were getting close to detecting gravitational waves, or soon after we detected them. And Brzezinski said to us, you need to develop a new technology, which he called quantum non-demolition technology. You want to make a measurement of gravity waves without having the quantum state of your detector be demolished and get in the way of the gravity wave measurement due to these quantum fluctuations. This is today, I think, beginning to be called quantum precision measurement technology, and it's a close cousin of quantum information science. It was a piece of quantum information science, close cousin of quantum computing and quantum cryptography. There are two quantum noises in a LIGO gravitational wave detector. One of them is the quantum fluctuations of the centers of mass of the mirror. Now, one of the reasons this project cost over $1 billion taxpayer dollars was that we had to isolate the mirrors so well that, that the laser beams would measure only the motions of the center of mass, and we would be insensitive to the thermal fluctuations that are inside those mirrors, for example. And so the fluctuations of the mirror center of mass fluctuating in opposite directions, squeezing along one arm and stretching along the other arm. This is one source of quantum noise, and the other is random arrival of the signal light as it's going into the photodetector at the output of the gravity wave detector. And so you have two forms of quantum noise. It was one of the great pleasures of being at a place like Caltech or Harvard, or the students who are more brilliant than I am, and more brilliant often than any of the professors. So one of my students, Carlton Caves, in 1981, who realized that both of those quantum noises are produced by vacuum fluctuations of light that enter the interferometer backwards. The laser beam sends light, the laser sends light in this way, so that's the input way. The gravity wave signal is carried by light going out to the photodetector. Vacuum fluctuations entering from this direction, they produce fluctuations when they beat against laser light, a pressure that pushes these mirrors apart while the corresponding pressure is lowered, so these mirrors move together. And so these fluctuations that are in the opposite sign in the two arms, the beating of the vacuum fluctuations against the laser light. And similarly, it's the beating of the vacuum fluctuations that, after being in the interferometer, leak back out alongside the signal light that give rise to the randomness in the arrival of the signal photons. So the same thing, the incoming vacuum fluctuations produce both forms of noise by beating against the laser light or the signal light. Now, Carl was really brilliant. He then said, we can reduce the noise, at least to some degree, this quantum noise, by manipulating the vacuum fluctuations. And in talking to you about this, having told you all about how the universe, expanding universe, manipulates vacuum fluctuations perhaps to create you and me, everything, all the matter in the universe, having talked about how vacuum fluctuations in the birth of a black hole produce Hawking radiation, then talking about how a very advanced civilization might use vacuum fluctuations to hold a wormhole open. Well, why shouldn't physicists manipulate vacuum fluctuations to control quantum noise in our gravity wave detectors? So that is precisely what Carlton Caves in 1981 told us to do. But it was then somebody else, Bill Unruh, at that time very young guy, a student of John Wheeler's, who had just gone to the University of British Columbia. He did a very careful calculation and realized that, in fact, if you did the squeezing in just the right manner, you could reduce both forms of quantum noise by more or less as much as you wished if you had good enough technology. There were no obvious limits to how well you could do this. It was a huge surprise. But then we were off and running. Carlton Caves told us what we needed to do, as elaborated then by Bill Unruh. Jeff Kimball, who was just down the hall from us at Caltech and was an optical atomic molecular physicist, superb physicist, he launched into perfecting devising and then perfecting techniques for squeezing. There was a big competition over how to do the squeezing in practice. This is the particular technique of manipulating vacuum fluctuations that needed to be done. But he invented the technique that has won out, that is now universally used. And then he invented the technique to manipulate the details of the squeezing in the manner that UNRWA showed that we really needed. This is modern quantum precision measurement technology in LIGO. It took 40 years of development by the LIGO team and others to bring that technology to fruition. Today, this is one of the main factors in enabling LIGO to see several collisions of black holes each week, by contrast with one collision every 6 weeks when we first turned on. As for the future of warp space-time research, well, that's in the hands of today's students, postdocs, and young faculty, while I focus on fun at the interface with the arts, as epitomized by my 2 recent books, The Science of Interstellar and The Warp Side of Our Universe. Thank you very much.
Kip Thorne is willing to take some questions and discussion from the audience for a while, and I think he'll call on people if you raise your hands. And we'll go till 7, say, if that's okay with you, Kip. Is that
That's
15
fine.
minutes? Is that okay?
Everything was so clear that there are no questions.
What is at the tip of the wormhole?
At the tip, in this case, it's the tip of the black hole. It is the singularity, in fact, in reality. And it's really probably the 3 singularities that I talked about. So this depiction is not a good depiction in reality. You have the chaotic singularity, you have that stretches and squeezes randomly, and you have the 2 shock singularities, and that's all going on inside. And this particular painting does not capture that. So, and that is part of trying to explain things, is you have to break it up into pieces. And if I tried to explain everything all at once with that in there as well, I would have not made any progress.
Professor Thorne, Roger Penrose talks about gravitation as affecting collapse of the wave function. I'm wondering if the gravitational waves that you're detecting in LIGO might affect the level of quantum noise differentially in the 2 arms.
So, did everybody hear the question? Yes? Okay, good. I don't think so. The gravitational waves, by the time they reach the Earth, are so extremely weak that the effect they have on the detectors is just superposed linearly on top of whatever is going on inside there. Roger's speculations are all related to situations that are quite different from what we're dealing with here, where we're just doing the very best we can with the most sophisticated technology that we've been able to devise to see a very, very tiny effect. And there's no reason, from my understanding of the physics, for the gravity waves to do anything except just superpose their motions on top of whatever the vacuum fluctuations are doing.
You said that for the first year and a half of your physics studies at Caltech, you felt like you were slower than the other students.
Oh, I know I was slower. I guarantee I'm slower than you are.
So what did you do to improve? And
So the most important thing that I did, I struggled. Let me just describe one aspect of the struggling. We took a lot of humanities courses as well as science courses, and so they gave us a speed reading test, and I read so slowly that they told me that I would never make it through my humanities classes unless I took a speed reading course, so I could speed read faster. So I went to the speed reading class for one day, and I figured I couldn't afford the time, and I abandoned it. That was great. I simply recognized I had to find some way that when I learned something, I held it in my mind. I didn't have to relearn it a week, a month, or a year later. And the strategy I developed, which turned out to be, for me, very fruitful, I used for the rest of my career, is whenever I learned something that was important in a notebook, I wrote down in my own words what that was, something related to physics. And then I wrote down in my own words or my own equations, I sketched a derivation of this or an explanation of this. And so if it had been written down in my own words and then the derivation explanation, my own, devised, having seen it talked about in a lecture or in a textbook, somehow it really stuck with me after that. And in fact, those notebooks became powerful tools for me when I wrote this more recent textbook with Roger Blandford called Modern Classical Physics. A lot of that comes from my notebooks when I was learning these subjects. Years later, I tried to learn plasma physics. I went to Cornell to work with Ed Salpeter. I was then in the middle of my career. And I used precisely this technique to try to get a grasp on plasma physics. That turns out to be much more complicated than relativity. So yeah, I sort of mastered it, but to the extent I mastered it was only by this technique that I could do it. Sorry. Thanks.
Hi. Thanks very much for the nice lecture.
Okay. Mm-hmm.
Hi. I have a question about the visualization of whenever someone is falling into the black hole. So we know that the expansion of null geodesic congruences changes when we are outside or inside of the black hole.
I'm sorry, I missed that. We know that what?
Yes. The expansion of the congruence of null geodesics is different whenever we are outside or inside of the black hole. Would we observe this effect in light?
So the gravitational waves, so for the audience who don't know the mathematics of this that you're asking about, the key issue is there are differences in how physics behaves inside the black hole than outside. There's a continuous behavior as you go across the horizon, but something changes sign as you go into the black hole. And can you see the effects of that in LIGO? The gravitational waves that we see in LIGO are all produced from outside the horizon. And it turns out they are produced almost entirely from a region, if the horizon is, say, this size, they're produced almost entirely from a region outside of here. Anything inside of a shell right around the horizon, those perturbations, those distortions of space and time, they become gravitational waves that go into the black hole, unfortunately. I would really like the gravitational waves from the very horizon to come flying out, but we know now from computer simulations that that's not the case. And so it's very hard to get information. It may be impossible to get information from the very close to the horizon because those waves go into the black hole instead of out. And so we're only seeing regions that are bounded away from the horizon by some finite distance.
Hi, thanks for the talk. I wonder whether you have any guess or expectation on what kind of new physics do you think gravitational wave astronomy can enable us to see or understand?
So in most cases, when a new way of observing the universe, such as X-rays or radio waves, comes along, there are big surprises. And we have had surprises in this case, but not really big surprises yet. I expect there will be big surprises, but I don't know when. There have been surprises. The black holes that we see are heavier than people expected to see. The populations of black holes are different. And the the observations of a black hole, of two neutron stars that collided and merged, the electromagnetic waves together with the gravitational waves showed us, I think to most people's surprise, that it's likely that most of the gold and platinum and other precious metals in the universe are made in those kinds of neutron star collisions. There had been speculations that might be the case, but I think it was really quite a big surprise for most people. So we've seen mild surprises so far, but not the really big surprises that I have been expecting. What I'm really hoping for is seeing the gravitational waves from the Big Bang, from the inflationary era of the Big Bang, and seeing whether or not they're the waves that would have arisen as a result of vacuum fluctuations of the gravitational field, swallowing expansion energy and turning themselves into the gravitational waves. I'm hoping that they're not what is expected, that there will be a big surprise there. More generally, however, there are a variety of things that will be seen with gravitational waves over the coming decades. We will expand into other frequency bands. Already, a technique called pulsar timing arrays is seeing gravitational waves with periods of order a year. Very, very low period, long wavelength gravitational waves that are probably from the collisions of humongously large black holes, but we don't know for sure. So we have now two frequency bands that gravitational waves are being seen in. We will see gravitational waves by other techniques in other frequency bands. And particularly interesting to me is something called the LISA gravity wave detector, which is a constellation of spacecraft in solar orbit that will be where the spacecraft will be moved back and forth relative to each other by a passing gravitational wave, and that'll be monitored with laser beams. This LISA mission, which is now a European Space Agency mission with some contribution from the United States. With that, I expect that we will see gravitational waves from small black holes or neutron stars orbiting around a big black hole in very complicated orbits due to the interacting of the vortices and tendencies of the great big black hole. And that motion, the waves from those motions will enable us to map with exquisite precision the full space-time geometry around the big black hole that's being explored by the little black hole as it orbits around and spirals into the big black hole. So things of this sort, that really, I mean, it'd just be fabulous if you could map the full space-time geometry like mapping the surface of Mars. And that may well come before I pass away at age 110. It may well come in the late 1930s. And I won't even be 100 yet. Okay.
One more, is that good?
Yeah, fine.
One more question.
Dr. Thorne, thank you very much for coming. Professor Gallison mentioned your enthusiasm for visualization in his introduction, and you talked about your interaction with the arts throughout the lecture. What do you think about the value of the visual, even if simplified, in communicating such complicated science to the public or even to scientists with other specializations?
So when I'm doing physics research, if I do it just with the pure mathematics, which is the language of nature as best we understand, it's a very, very slow process because I'm doing very complicated calculations, whether it's by hand or on a computer. And so I need to decide what kinds of calculations are worth doing and whether they're going to give me some real insight or not in order to explain some observations or predict some observations or probe some deep issue in physics. And so I need some way to have intuition about what goes on as a guide to my research. I need to translate the laws of physics into some form that is powerful for intuition. And the way I do it, the way many physicists do it, the way Stephen Hawking did it, is in terms of pictures. So for me, the laws of physics are embodied in mental pictures. And when I I give a lecture like this, and I show paintings like Leah's paintings. To a large extent, those pictures are, say, Leah's much more beautiful and much more compelling versions of the mental pictures that I'm carrying around in my head when I'm doing research. So for me, the research is a very visual process like that. And working with an artist on that, or with the visual effects company, Oliver James and his colleagues at DNAG, it's a process of making visualizations that will teach me a lot, enable me to communicate a lot, but it is, these are visualizations that are translations of the essence of what's going on in the equations. And so that's been my goal in the movie Interstellar, in my book on the science of Interstellar, in my book with Leah on the warp side of our universe. My goal has been to try to convey the essence, the most important ideas, as compellingly as possible through visualizations that resemble what I use in my research.
Thank you.
I want to thank all of you for coming, to thank our sponsors, the Gordon and Betty Moore Foundation, the John Templeton Foundation, and most of all, Kip Thorne.
Thank you.